Chapter 27, Part 1, we are going to look at creating confidence intervals for a linear regression. So back in Outcome 2, when we learned about linear regression, we used specific symbols to represent the slope and the y-intercept. When we were talking about the y-intercept, we called this b naught or b sub 0. That was our starting value. And our slope, we said b sub 1. Now, technically, this y-intercept and slope could change depending on our sample. If I ask 5 different students the same question, then my data is going to change, right? We've seen this sampling variability in all of our other models as well. So what we really care about is the true regression model, not just the specific model for the sample that I'm looking at, but the true model that fully represents the population. So since we're switching gears here and I'm not looking at just a specific sample, I'm looking at a population, my symbols are going to change slightly. So these are the parameters. These are what is representing the slope and the y-intercept for the population. They're very similar. Instead of b naught, we're going to use beta naught. So this is a beta, it's a Greek letter, looks like a B with kind of a tail on the end. So beta naught is our y-intercept, and then beta sub 1 is our slope. Now, the next 2 parts we're going to look at are both going to deal with this linear regression. So we're going to see these slopes and y-intercepts. We're going to work on 2 things here, creating a confidence interval and running a hypothesis test. What's nice is for both of those options, confidence intervals and hypothesis test, we have the same 4 conditions. So the first condition that we need to meet is that the scatter plot of our data must be linear. So the scatter plot of data must be linear. Now, oftentimes it's not going to be perfectly linear, and that's okay. It just needs to be roughly linear, more linear than it is curved. The next thing that we'll do is look at those residuals. Remember that the residual is the distance that your data point is from the line of best fit. And the first condition for those residuals is that each residual, or the residuals themselves, must be independent. So I'm going to give you just a random scatter plot here. If I have my data and I have my line of best fit, what we're doing when we're checking that the residuals are independent is I'm making sure that just because this data point was below the line of best fit at a small residual doesn't impact what's happening on the next dot. So this dot over here now has a positive residual and it's much larger, but this residual has no impact on this one over here. So those residuals are independent. The third condition that I'm going to check is making sure that my residual plot is evenly spread. So to check that, we are going to make a residual plot. We're going to make sure that the data is evenly spread out. I don't want to see kind of clumps of data here. And then the last thing I'm going to do is make sure that my residuals are nearly normal. So to check if those residuals are nearly normal, we have 2 options. We can either make a histogram or we can make a normal probability plot. We're going to end up using t-scores again here, and in order to use a t-score, I need to make sure my data is normal, so we check that normalcy by looking at my residuals. All right, the first thing that we'll look at is creating confidence intervals, and what we're doing here is creating a confidence interval for the true slope. So I'm going to change this. Right now it just says beta. I want this to say beta 1. So I'm looking for the confidence interval of the true slope. Okay, my formula says to take a good estimate of the slope, which would be my sample slope, which is B1, I'm going to add and subtract a t-score, and then I'm going to multiply by the standard deviation of B1. I do want to point out that sometimes the standard deviation is called standard error. Standard error and standard deviation really mean the same thing, but sometimes you're going to see standard error instead of standard deviation. Sometimes books write that as SE. It means the same thing as standard deviation. Now, when we're doing these problems, there are two ways that the information can be presented to you. The first option is that the data is given, so just raw data will be given. It'll be given in like a little XY chart here. We'll have all of our numbers. What we'll do in that case is use our calculator to create the necessary graphs to check the conditions. So we'll create a scatter plot, create a residual plot, create a histogram using that calculator, and then we'll use our calculator to complete the interval. There's very minimal algebraic work necessary when they give you the actual data. A lot of it, most of it, is just done straight on your calculator. Okay, the second type is if computer output is given to you. If that computer output is given to you, we're going to analyze the necessary graphs to check for the conditions, so they'll already have the graphs made for us, and then we can use that information provided to calculate our interval. So there will be a little bit more algebraic work necessary if the data is not given. Okay, let's go ahead and turn our page to look at our first example. Example 1 says marathons are typically, ideally, run in cooler weather conditions for the safety of the participants. We will use the data as shown from Chance magazine, which gives times and temperatures from the top female performance during the 1990s. Create and interpret a 95% confidence interval for the true slope. So what we're focusing on here is this true slope for this data. Now I'm going to start with inputting this data into my calculator. I'm going to put the degrees into L1 and the minutes into L2. And I'm clearing out anything else that's in there. Again, we're going to put those degrees in L1, minutes in L2. Go ahead and pause your video as we type this data in. All right, once we have that data in, I recommend creating a line of best fit just right off the bat so we have an idea of what we're looking at. So I'm going to go over to Stat, Calculate, Linear Regression. I want to make sure I'm pulling data from L1 and L2, and I can go down to Calculate. So again, when we're writing that line of best fit, I want to make sure I'm putting this in context. So I have my predicted minutes. Looks like my slope is, if I'm rounding, 0.03 times the degrees in Fahrenheit plus a y-intercept of 141.72. Okay, so this is my line of best fit, it's my prediction. What we're going to do is be analyzing this slope here, finding a confidence interval for the true slope. Now before I jump to my confidence interval, I do want to check my conditions. So the first condition is that the scatter plot of the data must be nearly linear. So I'm going to go to my stat plot, second y equals. I'm changing this to scatter plot, which is just that first one. Make sure you're pulling data L1, L2. And I'm going to zoom 9. Okay, let's go ahead and just sketch what we see. Okay, to me the data is looking just kind of all over the place. I'm not really seeing much of form here, but if I had to choose, I guess I would agree that this is somewhat linear. So I'm going to say the scatter plot of degrees and minutes is, instead of just saying linear, I'm going to say roughly linear. My next condition is making sure that the residuals are independent. So I don't think that this first time had any impact on the other times. So my residuals are independent. What happened one year shouldn't impact the other year. Okay, the third condition is making sure that the residual plot is evenly spread. I haven't made a residual plot yet, so I'm going to go ahead and do that. I'm going to go to my stat plot again, so second y equals. And instead of L2, I want to change this to residual. So we said to press second stat. Here's residual. And now I can zoom 9. Here's my residual plot. I'm just going to sketch that real quick. Okay, when I'm looking at that residual plot, I'm making sure that things are evenly spread. I'm not seeing any clusters or groups. So I definitely agree here. The residual plot is evenly spread. And my last condition, I need to make sure that these residuals are nearly normal. So again, I'm going to make another graph here. I'm going to go to my stat plot. I'm going to start with making a histogram. So I'm going to change this to histogram here. But I want a histogram of the residuals. So instead of L1, I need to again change this to say residual. Once I have it changed to histogram and residual, I'm going to press zoom 9 and I'm going to sketch what we see. Now that histogram isn't great. It's not horrible though either. It does look pretty normal to me. If you're unsure about that histogram, you can always make a normal probability plot. So I'm going to go back to my stat plot. I'm going to change it from histogram to normal probability plot, keeping the data from those residuals. Zoom 9. We can sketch this as well. So my normal probability plot does look pretty straight. My histogram looks actually pretty normal there. So I'm going to say that the residuals are nearly normal. Okay, all of my conditions are met, so I am good to start making this confidence interval. All right, now technically our formula for this says to take our slope, add and subtract our t-score times the standard deviation of the slope. Now we can find most of these things on our calculator, but it's tricky to find the standard deviation of the slope, not just the standard deviation of the actual data. So instead here, what we're going to do is just create this confidence interval on our calculator. So what we're going to look for is called a linear regression t-interval. So it's called a lin-reg t-interval. Linear regression because I'm focusing on slope, t for t-scores, and interval because I'm making that confidence interval. So in our calculator, we're going to go to stat, tests. I like to just scroll up, and that linear regression t-interval is almost all the way at the bottom. I have my data typed in, so I'm good to go there. Frequency, you can just leave as 1. Confidence level should match, so 95 looks good. You could store your regression equation. We don't need to worry about it though. I'm just going to go straight down to calculate. Hey, I do like to check and make sure this b value should match the slope we had in the very beginning here. And it does, 0.03, 0.03, so we're good. So let's just go ahead and jot down this interval. Did a little bit of rounding on that upper bound of my interval. Okay, once I have my confidence interval, the last thing that I need to do is interpret. Our interpretation is going to start the same as all of our confidence intervals. So I'm going to say I'm 95% confident that. Now what we are doing is interpreting slope. So if you think about that linear regression review we just talked about, we talked about how to interpret slope. Essentially, we're writing a confidence interval for that interpretation. So for slope, we said that for every additional x, we expect the y to change by an average of whatever. Okay, this right here is what we're expecting that y value to change by. So I'm going to say I'm 95% confident that for every additional, here's where I'm going to input my x variable. So my x's was looking at the degrees in Fahrenheit. So I'm going to say that for every additional degree in Fahrenheit, the minutes, and this was minutes to complete a marathon. So I'm going to say the minutes to complete a marathon will, here's what we'll say, either increase or decrease. I have both a negative and a positive, so I'm expecting it to decrease and increase. So I'm going to say that the minutes to complete a marathon will decrease by 0.0378 and increase by 0.0931. Forgot my labels here. These are both in minutes. And we're going to add on that this should be on average. Okay, so I'm 95% confident that for every additional degree in Fahrenheit, the time that it takes to complete a marathon will decrease by an average of 0.03 minutes or increase by 0.093 minutes. Okay, so based on our data here, we had a positive slope. So what we were saying is that as the temperature increases, we're expecting the time to increase. This confidence interval is telling us that although there was an increase in our specific sample, if I were to look at every person that's ever run a marathon, specifically looking at women here, I think it was looking at women. Yeah, female performers. Yeah, so if I just looked at women, I could see an increase or a decrease in their marathon time, depending on how that weather is changing. Okay, let's go ahead and look at one more example here. This one's going to be slightly different because instead of giving us data, they're going to give us the computer output. So example 2 says, concerned about test anxiety, a researcher enlists 24 student volunteers for a study. A psychologist interviews them before a math test, assessing their anxiety levels on a scale from 1 to 10. The table shows the anxiety levels and the exam scores. Create and interpret a 90% confidence interval for the true slope. Okay, here we have all of our data. We have the anxiety level and test score. And then in this box is where we have our computer output. Now there's quite a bit of important information in that computer output, so let's just kind of recap some of those. Most of them will tell you the dependent variable, so this is your y variable. It gives you your r squared. It gives you r squared adjusted, which we will never really need. But underneath it, it typically gives you degrees of freedom, which is very helpful. So our degrees of freedom is 22. Looking at the sum of squares, degrees of freedom, mean square, that stuff is not necessary. That's just telling you how they came up with this line of best fit. But where it starts to list the variable, coefficient, standard error, coefficient, probability, these are things that we will definitely need. So looking at our variable and coefficients, this part right here is going to help us create that line of best fit. So this is telling us our y variable was math score. So I'm going to put math score. That's my y. Your slope is always the number next to the variable. So our slope in this case is -4 point, rounding gives me 49. And that's times the anxiety level. Your constant is your y-intercept, so that's 91.66. This should sound familiar. This is the same data that we had with our little linear regression recap or review. Okay, a few other things that this computer output provides. It gives you the standard error of your slope or the standard deviation of B1, which we need. It's this right here, right next to the slope. That's the standard deviation. And then sometimes it'll say probability. Sometimes this last column will say p-value. This is the p-value that we would need if we were running a hypothesis test. Okay, in this case, it does provide us the actual data. I'm going to ignore it and pretend it's not there. It gives me, again, a residual plot, which is nice, and it gives me the math test versus anxiety level. So this is just the scatter plot for your raw data. Okay, let's go ahead and start checking those conditions. Now the first condition that we need to check is to make sure that the scatter plot of the data is linear. So I'm looking at this scatter plot over here of just the regular data. It's looking to me like it's somewhat normal, or I'm sorry, somewhat linear. So I'm going to say the scatter plot of anxiety and math test is linear. Next, I'm checking to make sure that the residuals are independent. I'm definitely thinking that each of these residuals is independent of the last one. So residuals are independent. Third, I'm making sure that the residual plot is evenly spread. Looking at my residual plot here, I'm not seeing any clusters or groups, so I will say that the residual plot is evenly spread. And the last one, I'm checking to make sure that the residuals are nearly normal. Typically, they will give you a histogram or a normal probability plot. This example did not, so I'm going to say I assume that residuals are nearly normal. Okay, my conditions are met, so I can start making this confidence interval. Okay, now my formula for confidence interval again is to take the slope plus or minus a t-score times the standard deviation or standard error of the slope. Now, last time I was able just to type this all into my calculator because I was given data. If you are not given the data and you are just given this computer output and a bunch of random pictures and whatnot, you are going to have to use this formula here to find that confidence interval. What's nice is we know almost all of this right now. So B naught is the slope. We have that slope right up here next to anxiety level. So my slope is the -4.49. Standard deviation of the slope I also have. That's the standard error of your coefficient. This coefficient I'm looking for is my anxiety level. So that standard deviation or standard error is 1.551. The only thing I'm missing at this point is the t-score, which I don't have, but I could do a little bit of side work here to find that t-score. Okay, off to the side, I'm going to draw my little t-model here. I'm looking for 90% confidence, which means there's 10% left, so 5% on each tail. I'm going to use inverse t here to find that t-score. To get inverse t, we're pressing second bars. The area is 0.05, and degrees of freedom can be a little tricky to find. It should be hidden somewhere up here in that computer output. In this case, my degrees of freedom was 22, so I'm going to put 22 there. So I had 0.05 and 22, gives me a t of 1.72. So I'm going to go ahead and put that 1.72 into my confidence interval. I'm going to start with finding this right-hand side, my margin of error. And I'm going to go ahead and subtract and add. Once I have my interval again, I can go ahead and write my interpretation. So I'm going to say I'm 90% confident that for every additional x value, which my x in this case was my anxiety level, so I'm going to say that for every additional level of anxiety, the test score will, these are both negatives, this one's a little bit easier, so I'm going to say that the test score will decrease by an average between 7.158, and this is a measure of the test score, so I'm assuming that that's in a percent, so it's going to decrease by an average between the 7% and 1.822%. So I'm 90% confident that for every additional level of anxiety, we expect the test score to decrease by an average somewhere between 7% and 1.8%.